In Module 4.1 we got a very quick overview of how a scanning tunneling microscope works. Let's look at it in more detail here. So this figure here shows a schematic electronic circuit for controlling a scanning tunneling microscope. And of course these days it's all coded in digital control systems. But let's take a look at this circuit because we can understand some of the factors that go into controlling any scanning probe microscope. In order to understand this schematic, though, you need a little bit of electronics background. So let me introduce you to a marvelous thing called an operational amplifier. These are very high gain chips with field effect transistors at their input, so they take essentially no current, and their gain is almost infinity. That means that even the slightest voltage difference between these two terminals, one a non-inverting terminal, in other words, if this voltage goes up, the output goes up, the other an inverting terminal, in other words, if this voltage goes up, this voltage goes down. And so if feedback is applied between the output and the input, and to the inverting terminal, then the voltage at this point will always be adjusted so as to be precisely equal to the voltage at this point. Any departure from that will cause a correction which would then appropriately lower or increase the voltage at this point so as to make these two equal. So let's go around this circuit. The first element you see here is a current to voltage converter. So in this arrangement, the sample itself is held at some particular bias with respect to ground. The STM probe is connected to the input of an op-amp working as a current to voltage converter. So this non-inverting terminal is grounded, which means that this terminal here will be held at ground by the negative feedback. And that means, therefore, if this output is sitting at V0 and this resistor is R, then the current flowing into this point must be V0 on R, and that has to be exactly equal to minus the current flowing in from the scanning tunneling microscope probe. In other words, this is a converter that gives you a voltage output, V out, equal to minus I from this STM probe times the value of this resistor. So the current's now be converted to a voltage. What's the next element in here? The next element is an integrator. In this element, the feedback component is a capacitor. And recall that no current flows across a capacitor unless the voltage here is changing with time, in which case the current flow here is given by the capacitance times the time derivative of the voltage change at the output. So if there is a difference between this input, V0, and the set point here, then this will cause a current to flow until these 2 points are equal, and it'll do it by generating a ramp in voltage. So the output will go up like this, and then stop once V set is equal to V0. This is the control element that keeps the scanning tunneling microscope constant, and its response time is on the order of 1 over RC. Now let's go on to the final element in this circuit, which is an amplifier. So it has a resistor I've called R3 here, going into the inverting terminal once again, and a feedback resistor I've called R4. So if I put an input voltage here, the current flowing in, remember this point is at a virtual ground, is V in over R3. That has to be equal to minus V out over R4. So in other words, V out over V in is just given by minus the ratio of R4 to R3. So this can be a high gain amplifier that will drive the piezoelectric element through a large excursion. The phasing of the whole loop around here, or the polarity of the piezo, is chosen so that if the current here increases above the set point, the result will be a voltage that moves the PZT away from the sample, thus reducing the tunnel current. This motion will continue until the error signal is 0, again with respect to the set point, and then it will sit at that new point. So this signal coming out here is a measure of the height of the probe, and it's what modulates the brightness of the display. Ramp signals here scan the PZT in the X and the Y direction and are also applied to the display. So the spot on the display moves synchronously with the probe, and its brightness is a measure of the height of the probe. The scanner itself is usually made out of a tube rather than the rods you saw in section 4.1. So if we take a look at a tube scanner and draw a cross section like this, there will be one electrode coated on the inside, another coated on the outside, and a bias applied between these. Typically, the response of a slab of piezo material with electrodes here and here is to expand and contract in this direction by about 3 angstroms per volt applied. However, because of the tube geometry, and remembering that this material has to pretty much keep its volume constant, if we contract the walls of this tube, then the length must increase. And rather like squeezing on a tube of toothpaste, there is a geometrical amplification to conserve the volume of the toothpaste, and in this case the volume of the PZT. That means that the sensitivity in this mode is often on the order of 30 angstroms per volt. The scanning in the XY direction is done in a very simple way in scanners like this. The external electrodes are segmented like this, and so for example if this is the X direction we would apply a plus Vx here and a minus Vx here, and then the inner element might be grounded like this. This would then result in one part of the tube expanding and the other side contracting, with the result that the tube bends to move the probe in a dimension perpendicular to the axis of the tube. So here is a real ultra-high vacuum scanning tunneling microscope. You can see the scanning element here and a sample plate that is easily replaced sitting over the probe, heating elements here that allow the whole system to be heated, and wires that carry the signals out of the STM. One final point we need to talk about is vibration isolation. You saw the very elaborate vibration used many years ago in the movie in 4.1. It's actually not necessary. As we show in Appendix D, the response of a driven damped harmonic oscillator falls off approximately, so this is the movement of the tip owing to vibrations, here's the amplitude of the vibrations, F is the frequency of the vibrations, and F0 is the resonant frequency of, let's say, the piezoelectric element, typically the lowest frequency resonance in the microscope, squared. For a well-designed STM, the lowest resonant mechanical frequency is perhaps on the order of 20 kilohertz. It's fairly easy to do this. By suspending the microscope on bungee cords, you can guarantee that no building frequencies greater than about 1 hertz reach the microscope, and therefore the suppression of vibrational amplitude is on the order of 1 over 2 times 10 to the 4th squared, or some fraction of 1 billion times. That means that if the vibrational amplitude is even on the order of millimeters, that the actual displacement of the probe is on the order of picometers.